Before we start coding the device, we have some preparations to make. First, we need a microcontroller that supports USB. I use a black pill development board with an STM32F401. Of course, we need an IDE to work in. I will use STM32Cube IDE and CubeMX code generator. Now, I won't be explaining how to program a microcontroller in general, it's a totally different topic, so you're expected to have this software already. If you're not familiar with it, it's free and there is plenty of tutorials on how to install and use it. Next, we need a Linux machine to run the driver. I will be using a different machine, so I'll be switching to it from time to time. This Linux machine needs to be using some monitoring software to see actual USB requests and the device's responses. I'll be using a program called Wireshark. This program is primarily used for watching network traffic and it does not support USB out of the box, so we'll need to load a module called USB Monitor or USB Mon for short. To load a module in Linux, one may use one of two commands listed here on the slide, ins-mode and mode probe. The difference is the first command loads a single module, while the second loads a module along with its dependencies. In later videos, when we develop our own module, we'll be using this first command since it won't have any dependencies. In case of USB Monitor, I'll be using the mode probe command. Another debug feature we'll be using is the one for the microcontroller. The thing is, USB transfers must be processed very quickly and we won't be able to place a breakpoint and inspect program step by step. Instead, we will configure the microcontroller to send text messages to the IDE. The feature that does it is called Single Wire Output or SWO for short. To enable this, we must first find the pin in the microcontroller that's responsible for this function. Here on the slide there is a screenshot from the datasheet showing that the SWO capable pin on my device is PB3. The other photo shows this PB3 pin connected to the ST-Link SWO pin. After the hardware connection is done, we'll have to configure the software. Specifically, we'll need to enable the feature in the IDE, which I'll demonstrate later in the coding section, and override the functionality that's responsible for printing things. The function that does printing is printf, of course. This function uses another function called _write as its lower-level implementation. Later in the coding section, I will redefine this write function so that microcontroller sends data through its SWO pin through ST-Link programmer back to the IDE. That is all theory for now. Let's move on and create the project. Here I have the STM32CubeMX opened. I will go to the MCU selector and find mine. Here I need to do a couple of things. First I need to enable USB. It is down here in the Connectivity tab, USB OTG FS section. Select Mode Device Only. Next we need to configure debug method, which is SVD in my case. Under System Core, sysdebug, choose System Wire. Next we need to configure GPIO. My button is connected to pin B10, I am setting it as input. The LED on this board is connected to pin C13, I am setting it as output. Now adding pull down to the button pin. Next we need to configure clock source. Internal oscillator is unable to generate the needed frequency. Here under RCC high-speed clock, choose crystal resonator. My board has a 25 MHz crystal. Now here under clock configuration we need to make sure that it does not contain errors. The system asks if I want to let it try to fix clock issues, I agree. And we see that our external oscillator is chosen, main clock is 16 MHz and most importantly this 48 MHz clock is configured correctly. Next I go to the Project Manager tab to set the information about the project. I'll make up a name, my IDE is Cube IDE, and we are ready to generate this code. Now when it's done, I choose to open project. After a little while the project is loaded and here I am opening the main file. I built the project to verify that it does not contain errors. It seems fine. Now, first thing I'd like to do is to enable the single wire output, a feature that allows us to see logs inside the IDE console. For that I need to define this _write function I've copied from another project because honestly I don't remember nor its prototype nor its contents. This function will be called by the printf function, so we're overriding the default behavior of the printf. Of course I also need to include this stdio header to use the printf. When it's done I can print a string somewhere inside the code, make sure not to forget the new line character. It will be visible inside the IDE. Before testing it I have to enable it, but first let's see if the code built so far. I run the debug, leaving configuration as it is, and it seems to run fine. I'll click continue and pause execution to make sure it stops inside the main loop, not inside an error handler. Now I'll configure the single wire output. Here in the debug configurations, make sure your project is selected and go to the debug tab. Down here under serial wire viewer, click enable. To open the console that shows the logs, click window, show view, SWV data console. It will appear down here, then click this configuration button, enable port 0 and click OK. Lastly, click this round icon to start capturing the logs. Now if I continue execution I should see the device saying hello. This feature simplifies debugging by far, especially in the USB case. Now that it's working, we're ready to move on. In the host side, we'll need a program called Wireshark that allows us to see the USB traffic to and from the machine. It's really simple, we just need to install a couple of packages. I always forget their names, but it's easy to find online, for example in this Stack Overflow answer. I'll need my terminal window and I'll reorganize Windows a little bit. So I need to install the Wireshark itself and the library called libpcap. The rest of the answer is devoted to adding your user to the group of Wireshark users. I won't do that, I will just call Wireshark with sudo. But before opening the program we'll need to insert the USB mon module using modprobe command. Now run Wireshark, and here we have a bunch of USB capturers. I will select one of them. Here is all the USB traffic through this machine. We can filter the messages by the device here in the filter prompt. For example, when I know that my device is assigned number 3, I would enter usb.deviceAddress == 3. Down here the list would contain only traffic to and from my device. I'll stop the capture now. Next we'll need the Linux kernel sources. I can find them on GitHub. This repository from Torvalds, the author of Linux, is the one. I'll close this Wireshark window, we won't need it today. Before downloading the sources, we need to know what version of the sources we need. Well, I'd like to download the sources for my Linux kernel I currently have. To find out my current version, I'll type command uname-r. It seems to be 5.15.0. Here in the GitHub repo, there is this text button, click on it. It shows the list of all the releases of the code. I need to find mine. It happens so that I can enter some version here in the search prompt. Hopefully it will get me to the right page. I'm entering 5.15, going through neighboring pages, and here it is, my version of the source code. I'm clicking on the zip icon to download the archive. As you can see, I have actually downloaded it already, so I'll cancel this one. I'll open the one I have and unpack it someplace. Alright, here it is, and actual USB code is located here under drivers, USB somewhere down here, and core. This folder contains most of the code we'll be using. That's it for the preparations. Next time we'll start writing the code for the device.